The architectural blueprint of arrays. An array is a linear collection of elements stored in contiguous memory locations. Its simplicity lies in its uniformity. Each element occupies the same amount of space, enabling direct access via indexes. This property, known as random access, allows time complexity for retrieval, making arrays ideal for scenarios requiring instant lookups. However, this strength comes with limitations. Resizing an array typically requires copying all elements to a new location, resulting in time complexity. Dynamic arrays address this by allocating extra space proactively, but the overhead remains significant during expansion. Understanding these mechanics is vital before deciding whether arrays suit your needs. Mechanics: arrays are declared with a fixed size, often determined at compile time or initialized dynamically. In languages like C++, manual management is required, whereas higher-level languages abstract this through libraries. Memory alignment ensures predictable cache behavior, enhancing performance in tight loops. Demonstration: consider a sorting algorithm using bubble sort on an unsorted array. Since elements are accessed sequentially, caching mechanisms benefit from locality, reducing fetch latency. This contrasts sharply with less spatially local data structures like trees or graphs. Pros: fast indexing, predictable memory usage, compatibility with low-level optimizations. Cons: fixed size limits scalability, inefficient insertions/deletions in middle positions. Arrays excel in applications requiring random access and minimal mutation. Image processing frameworks, scientific simulations, and game engines frequently leverage arrays due to their deterministic nature and hardware-friendly memory patterns. Linked lists: flexibility meets trade-offs. A linked list consists of nodes connected via pointers. Unlike arrays, it does not require contiguous memory, allowing dynamic resizing without copying elements. This flexibility makes linked lists invaluable when dealing with unpredictable data volumes or frequent modifications. Each node stores data and a reference to the next node, forming a chain-like structure. While accessing arbitrary elements takes time, a stark contrast to arrays. Insertion and deletion become significantly faster in certain contexts. This duality defines the decision-making process when selecting between the two structures. Internal mechanics: pointers introduce overhead, consuming additional memory for tracking connections. Garbage collection becomes necessary to manage orphaned nodes, adding execution cost. However, this overhead is negligible compared to the benefits gained from dynamic sizing. Use case example: a music playlist manager might use a doubly linked list to allow bidirectional navigation. Inserting a song at the beginning or midpoint involves simple pointer updates rather than expensive block rearrangements typical in arrays. Pros: efficient insertions/deletions, no pre-allocation required, supports sparse data distribution. Cons: poor cache utilization, slower access times, increased memory fragmentation risk. Performance benchmarking reveals that for small-scale applications, linked lists may lag behind arrays due to indirect addressing. However, as dataset sizes grow or modification rates increase, the advantage shifts decisively toward linked lists. Benchmarking battle: array versus linked list performance. To truly understand their strengths, we analyze common operations side by side. Consider insertion at position k for a dataset of size n. An array demands shifting nk elements, yielding time complexity, while a singly linked list achieves it in time through pointer manipulation. Searching operations tell a different story. Searching for an item in a sorted array via binary search gives logarithmic time, but unsorted searches remain linear regardless of implementation. Conversely, searching a linked list is always negating potential speed advantages in specialized scenarios. Real-world metrics: empirical tests show that arrays perform approximately 15 to 20% faster than linked lists for traversal-heavy workloads, primarily due to CPU cache hits. For insertion-intensive tasks like maintaining a queue system, the gap reverses dramatically in favor of linked lists. Caveat: These numbers vary depending on language specifics. Languages with automatic memory management might obscure performance differences caused by garbage collection pauses or virtual machine overheads. Best fit, arrays when indexed access dominates, linked lists when sequential manipulation is preferred. Hybrid solutions. Some systems combine both, such as Python's list type, which uses an underlying array with amortized insertions. Design choices depend heavily on the problem domain. Real-time systems prioritize predictability, making arrays preferable despite occasional inefficiencies, whereas applications with evolving data models lean toward linked lists. Memory management nuances. Underlying memory architecture influences data structure efficacy deeply. Static arrays reside entirely in stack memory, enabling quick allocation and release. Dynamic arrays, however, occupy heap memory, necessitating careful resource management to prevent leaks. Linked lists inherently use heap allocations for individual nodes, increasing pressure on the memory manager. Fragmentation issues arise as allocated blocks scatter across the heap, potentially degrading overall system performance. Techniques like arena allocation aim to mitigate these effects. Variations. Implementations differ widely. Singly linked lists suffice for one-way navigable data, while doubly linked lists permit backward movement at the expense of double the storage. Skip lists further optimize search by layering nodes strategically. Case study. Operating systems utilize linked lists extensively for task scheduling queues. Each process entry maintains links to predecessors/successors, facilitating context switching without relying on index-based queries. Stack allocation advantages. Faster access times, automatic cleanup, reduced memory waste. Heap challenges, increased indirection, potential delays, and memory leak risks. Selecting between static/dynamic allocations hinges on lifecycle expectations. Short-lived objects thrive in stack memory, whereas long-term constructs demand heap resilience against program runtime variations. Language-specific idioms and libraries. Different programming languages offer varying abstractions for arrays and linked lists. Java's ArrayList encapsulates dynamic array behavior seamlessly, while linked list implements doubly linked lists with optimized methods. C++ provides raw array capabilities alongside standard template library, STL, containers like vector, dynamic array, and list, doubly linked. Careful use of iterators enables unified access patterns across diverse structures. Python quirks. Although Python lacks built-in linked lists, third-party modules simulate them. Native lists behave like dynamic arrays, with insertions triggering occasional resizes that amortize overhead efficiently. Example contrasts. In JavaScript, array manipulations are handled natively, leveraging prototype chains for extensions. Node.js, however, employs linked list structures internally for asynchronous event loop coordination. Higher-level abstractions reduce boilerplate code but conceal implementation intricacies. Low-level control offers maximal customization but increases error proneness. Mastering idioms in your chosen language is crucial. Proficiency transforms vague knowledge into practical expertise, enabling informed decisions during development cycles. Advanced applications and hybrid approaches beyond basic CRUD operations. Advanced implementations exploit hybrid models. Hash tables often pair dynamic arrays with chaining via linked lists to resolve collisions gracefully. Similarly, B-trees blend array-indexed nodes with child pointers to optimize disk access patterns. Tree traversal optimization. Depth-first search routines frequently employ stacks implemented as arrays for LIFO behaviors. Meanwhile, breadth-first strategies rely on queues constructed with linked list principles for FIFO sequences. Amortization strategy. When implementing insertion logic in dynamic arrays, spreading resize costs across multiple operations reduces effective cost to near constant time. This principle underpins many high-performance library designs. Understanding how advanced data structures interleave array and linked list traits opens doors to sophisticated solutions. Design patterns like the decorator or adapter pattern enable structurally independent enhancements. When to combine memory-constrained environments, heterogeneous collections, adaptive algorithms, risks involved, increased implementation complexity, debugging difficulties, maintenance overhead. Evaluating trade-offs becomes second nature once you grasp how combinations can yield optimal results. Always weigh gains against added complication before proceeding. Educational pathways and practice recommendations. Building proficiency begins with deliberate practice. Start with core operations, gradually progressing to edge cases and degenerate forms. Coding exercises focused on inserting/deleting at specific positions help cement conceptual clarity. Suggested exercises: implement custom array/list classes with varied functionalities, like reverse iteration, sublist extraction. Benchmark their performances under controlled conditions to see theory manifest practically. Learning resources: Coursera courses on algorithms, Geeks for Geeks tutorials, LeetCode contests, all provide rigorous exposure to structure manipulation scenarios. Online judges like HackerRank enforce coding discipline systematically. Coding interviews often test ability to re-implement standard structures from scratch, gauging deeper comprehension beyond surface knowledge. Regular participation sharpens reflexes needed during whiteboard sessions. Studying patterns: observe how top-tier companies implement their APIs, learning from established practices. Peer review: engage with open-source projects, reviewing contributions to gain collaborative insights. Cultivating a habit of reading academic papers strengthens theoretical grounding. Seminars and workshops hosted by university CS departments also prove immensely beneficial for advanced learners. Future directions: emerging trends and research frontiers. Ongoing research continues pushing boundaries in data structure evolution. Non-blocking concurrent data structures aim to minimize lock contention in multi-threaded settings. Persistent data structures support versioning while retaining historical states, an area gaining traction in functional programming paradigms. Nanostructures and quantum computing: as computing transitions towards quantum architectures, rethinking traditional memory layouts presents intriguing challenges and opportunities. Quantum entanglement offers novel ways to parallelize operations currently constrained by classical physics. Machine learning integration: adaptive data structures responsive to ML feedback loops represent emerging frontiers. Reinforcement learning techniques optimize tree rebalancing or memory allocation policies autonomously. Gaming industries experiment with graphics acceleration through GPU-accelerated array transformations, exploiting massive parallelism available on modern cards. Such innovations redefine possibilities previously deemed computationally prohibitive. Current focus areas: energy-efficient computing, fault tolerance, distributed consistency models. Long-term implications: redefining storage hierarchies, challenging Turing completeness assumptions, exploring biological analogs. Remaining abreast of developments ensures your skills evolve alongside technological progress. Open-source communities and AR14 preprints serve as fertile ground for discovering cutting-edge methodologies. Conclusion arrays and linked lists represent two sides of a single coin, each optimized for distinct computational narratives. Their study unlocks deeper insights into algorithm design, memory management, and problem-solving philosophies that transcend mere syntax. Action step: begin today by analyzing existing implementations in your favorite language. Try modifying them incrementally, observing behavioral changes as parameters shift. Document lessons learned in a personal journal to reinforce retention and discovery of subtle nuances.